and find out what matters. So if we got the 1 or 2 factors that are really important, then we can have 10 levels in each of these and really do a detailed analysis. So we're doing screening, we're doing multi-factors, but we're really sadly limited because these experiments take a long time to run or set up or whatever. So not only are we, now we're in the worst of worst. Instead of doing all of them under the same background, or like we did in the following chapters, maybe we couldn't do them all under the same background, but we could at least do them all under different background conditions. We're even worse. We can't even do them all. And so that's the setup we are. So we're trying to do a screen with a low number of levels, a lot of factors, but we can't even do them all, so we're only going to do a part of them. So remember, we busted things up into blocks, but we can't do all the blocks, we're just going to do one of the blocks. And last week we were trying to decide which block to choose so that we didn't confound or confuse our main effects, because at least that's what we're trying to look for, okay? And so what's happening today is we want to make sure that when we do pick the block we pick, that we don't get this aliasing problem. And so we have to kind of understand what aliasing is. And we talked about it a little bit last week, and let's see, maybe it's easiest. I'll talk about it in the context of this, and then I'll talk about it in the context of signal processing and see if that clears it up. But the thought in words, what aliasing is when you cut out pieces of data for whatever reason. Maybe it's because of in the signal processing world, it's your sampling rate. In this world, it's because we don't have all the blocks. We're picking a certain block. Then some of the things that we throw out may look like the thing we're trying to measure for whatever reason. In the signal processing world, it's called as how you sample. And if they look like the same thing you're trying to sample, say for example, a higher level interaction like ABC looks exactly like A because of the way we pick the blocks, then its information is just going to add to A, and it's going to really distort how much A, the effect of A is because you've added it to it. Now, that may not be clear, and I think it will be clear when I show you the signal processing example I got. But let's look at it in this context, at least for the first 4 or 5 pages, and see if it makes sense. And if it doesn't, remember, I'm not going to really hold you strongly to this. I think it's just an interesting topic, but we're getting deep in the weeds in design experiments. So again, our scenario is, we've already lost some effects because of the confounding in the blocks, the way we had to set up blocks and throw things out. We're going to lose more by not doing all the blocks, okay? Let's see, we've got lots of factors, we've got a lot of higher order interactions, and these are terms, we can waste. We can throw them into, error terms and things. Remember, the higher order interactions are even hard to describe. What is A, B, C, D, E? They're, like I said, they're insignificant or difficult to explain or interpret. So we don't mind throwing an A, B, C, D, E interaction with an A, B, C interaction, mixing them in there and throwing all those things into an error term. But boy, we really, since it's a screening experiment, we really want to find out, does A matter, does B matter, does C matter? So we'd like to not confound those, like we talked last week, and we'd like to not alias those if we can. If we want to have confounding and aliasing, let's have that happen down in these higher order effects. Throw it into the things we don't care. So remember again our setup. At the 2F, we have 2 levels, low and high. 3F, 3 levels, low, medium, and high. And F is our number of factors. Remember A, B, C, D, E. And in my Google Little Box experiment that we talked about today, I'll give you A, B, C, and D, 4 of them. It's something physical. So maybe you'll really further appreciate what a factor is and how it can relate to the real world. So let's go back, and so we're gonna set the stage here. So we'll go back to chapter 8, where we had that example where we had three factors, 2 levels, and we had 2 blocks. And so that was the opening example, if you will, in chapter 8. So we had 3 factors, A, B, and C, and we set it up to where we chose to confound ABC with our two blocks. And remember, block 1 was this block, where that was both of them low, and block 2 was this block. And then we looked at the signs. Remember whether A was high, A is high, B is, you know, in relative to block 2, whether A was high here, here, or B and C is low. We looked at all the pluses and minuses. This column was the product of those. Yeah, and so let's see. So I'm looking at the pluses and minuses, and I'm looking, let's see, this is as it pertains to block number 2. Okay. And so the comment we made back in chapter 8 was, look, since the ABC interaction term had all the same sign, that meant when we compare block 1 to block 2, the ABC interaction was confounded with the block effect. So it's okay. So, and that's what we wanted to do. Okay, but let's look at some of the things in terms of block 2. If we just chose block 2 all by itself, so we know we've confounded ABC in block 2. But let's further say, you know, remember this scenario is I'm not even going to do 2 blocks. I'm only going to do 1. So let's just postulate that. Well, we're going to try just choosing block 2, and now we can't do block 1 because we don't have time. All right, well, look at the signs of A and the BC interaction. Plus, minus, minus, plus, plus, minus, minus, plus. And the signs of the B and the AC interaction, minus, plus, minus, plus. Okay. And the signs of C and the AB, minus, minus, okay. So there, as far as, you know, when you raise, you know, remember the pluses and the minuses is whether you put it at the high level or the low level, whether you make the change or not. So as far as this goes, if you're just looking at block 2, these are together. You know, I've set, like for example, A and BC. I've got A high and I got BC and a minus and a minus and a minus and a minus. So they're gonna combine. They're moving the same direction. So whatever change is due to A is also going to be added or subtracted just like BC, and the same with B and AC. You know, they're going to move together. So they're adding together. They're aliasing. They look, as far as in this block alone, they look the same. Now, if we went to the other block where the signs reverse and stuff, remember, okay, yeah, we can compare and say that there's difference, so we can get some, I have a change. You know, basically what I'm saying is there's no difference between those. So those are what's called aliases. Yeah, the A and BC are indistinguishable, B and AC are indistinguishable, and so are C and AB in terms of a change. They move together, and so you won't be able to differentiate it. Okay, so let's see. So in this context, so the sum of the square of the A is going to be the sum of the squares of BC, the same. They're going to be combined. So these are aliases. So let's see. So let's I guess, I said in my notes, go to Wikipedia. So let me try to do that to give you an idea of what an alias is physically, because this is really the value, I think, of this lecture. Let's look at Wikipedia's version of alias, and then I'll look at my sheet too. Has everybody seen? Oh golly, yeah, we could do that. Has everybody seen an alias before, or do you know what it is from a signal processing viewpoint, or is this like completely new to most people? Completely new. All right, let's see. Come on, Wikipedia. I'll tell you what, there it is. We'll do that, and I'll just go. Maybe aliasing, how's that? I can't let's go back. Let's see. I can type in the whole thing. Go back one more time. Let's see. Just got to do this thing. Let's see. How's that? That ought to do it. Yeah, there we go. Thank you. That's the big paper. Okay, so from a signal processing view here, let's look at this little picture here. And this is what I was trying to draw last week. I've got a signal that's made up of two sine waves, one kind of slow and one at a higher frequency. And this signal's, I may have others, but let's assume it's a real simple signal. It's got two sine waves. And I'm measuring it with a data acquisition system that can only sample at these major numbers, whatever this is. Let's say it's 1 second. It's a slow, dumb computer. So I sample here, and I sample here, and I sample here, here, here. So the little dots represent the data I'm measuring. Well, if you look, the little slow blue sine wave looks precisely and exactly like the red sine wave at those data points. Now, I guarantee you the red one looks a lot different everywhere else. But at the sample rate, they look the same. So the blue and the red are completely indistinguishable from the data acquisition's viewpoint. How can it tell the difference? You can't. If I just gave you those points, you'd say the red was the blue, or the blue was red. It wouldn't matter. So if this signal is made up of the blue and the red, and a bunch of other signals that are even multiples, the energy content, if we were going to do a Fourier transform and try to say, well, how much energy is in the blue frequency, how much energy is in the red, how much energy is in the next harmonic, etc., it's going to be messed up at this frequency because this blue one's going to have some energy, but it's also going to be added to the red energy because I just told you that the computer system can't tell the difference. And so that's what an alias is. So all these higher order frequencies, and this would happen at a different frequency too, right? If I sampled differently, it just moved it around. So all these higher order energies are adding to this one and distorting what the answer is. And if you're trying to look and see how much the energy is at different frequencies, like you do with a fast Fourier transform. In fact, what this little thing here shows, it's interesting. Took me a minute to figure out what it was doing. You've got a signal. This is your signal here, and you're adding to it this slow sine wave, a faster sine wave, and this noise stuff down here that's a sum of a bunch of higher frequency things. And it shows you what this added signal looks like at different sampling rates. So at a high sampling rate, here's what there. It looks good. It's a sine wave, slow sine wave with noise on it. But as you get lower and lower and lower and lower, it gets all distorted. You can see it's messing up your signal because it's these higher order things are adding in, and when you're trying to reconstruct it, it looks bad. In fact, physically, you can kind of see aliasing in this picture up here. Where this is a photograph of some bricks that was sampled properly. It's got no aliasing. Down here, when it's sampled such that the sample rate's wrong relative to the pixels, you get this moire pattern where that's not real. So you can actually, it comes up physically in many things. But the biggest area is signal processing, where you've messed up your magnitudes at frequencies because of the higher frequency term. So you have to do things like maybe throw it through a low pass filter or something, so you throw all those higher frequency terms out, or mathematically you can do anti-aliasing. I first got exposed to it when I was doing my PhD and trying to model heat transfer in the body, where I was doing that cancer research, and they were heating the cancerous tumors, and we couldn't solve the heat transfer model fast enough with a finite difference or finite elements to use it to control the heating of the tumor. The darn treatment will be done by the time the Fourier series, the finite difference model was done. And so there was a new mathematical technique at the time called spectral methods, and we had one of our professors was actually a big guru in it, so I took his class, and it was a way to model the thermal performance in a volume or an area or whatever. Instead of using finite differences and stuff, you could use Fourier transforms, and so you could take the partial differential equation, turn it into a differential equation, and then go back to the partial differential solution. But you had to do a bunch of FFTs, and so I had to learn mathematically how to anti-alias, because even then, if I was going to do a Fourier transform of a mathematical solution, it was poisoned like this, and so you had to clean that up before you solved it, or you were messing up your solution. Let's see, maybe I can do, maybe this is a good spot one more time to show it to you in a different way. because we're here, let's see. Yeah, here, let's look at it this way. So I've got an Excel sheet where I did the same thing you saw in Wikipedia. Okay, I did it first before I went there. Okay, so I've got a slow sine wave, the blue one, and a fast sine wave, the red one, and I'm sampling at the green dots. So again, I've set up the same issue where my sample rate, at my sample rate, the blue sine wave and the red sine wave look just the same. And what I've done over here in these columns, I've just made data. This is the blue sine wave, or the other way around, I guess. This is the red sine wave, that's the blue sine wave, and I'm showing you where I sampled. I just made that so I could plot the green dots. Okay, and so what did I do? So I sampled the data at those, it's not very much data, see? Okay, and I sampled at the 8 points. Okay, and I did a fast Fourier transform with Excel's Fourier analysis. Okay, so I just said, let's do a fast Fourier transform. So let's see. Here's a fast Fourier transform of F1, which was the red one, and here's a fast Fourier transform of F2, which is the blue one, at those sample points. Okay, so only at the green dots, and you can see we won't worry with what the meaning of the fast Fourier transform is, but you can see that from Excel's viewpoint, sampling those 8 data points. In fact, you can look at the 8 data points and see why I did that. There's no difference. It gave you the same fast Fourier transform for both signals, and big surprise, right? Look at the data. I mean, the data is set for the oddness in what they call 0. The data looks the same. No wonder Excel gave you the same thing. And by the way, this Fourier transform thing is just under your data analysis if you want to use it. And so it's telling you. This one's telling you it's all at 1 frequency. This is 2. It's at the blue frequency. Now, but the point I'm trying to make with this is all along is let's add both signals together and see what the fast Fourier transform is. Yeah, you see it doubled the energy content. So what I'm saying is, if the red is a bunch of noise, a bunch of garbage, and the blue is really what you were looking for, well, I really messed up my blue. Now, I know, I understand my red and my blue are the same amplitude, and in general, if the red's a bunch of noise, it might have lower amplitude, but maybe not, or maybe it's not that much lower. Either way, I'm contaminating and polluting what I'm looking for with these higher frequency things, and you've got to somehow deal with it. And directly, mathematically, you can see that's what it did. Doubled the energy content, and which is not real at all. You know, that's a high frequency noise that I didn't care about. And so this is the same thing. Now I know this is signal processing, we can maybe understand it, but this is the same thing that's happening to us now in the design of experiment world because of how we set up our block. We can't distinguish these two effects, the A and the BC, or the B and the AC, just like we couldn't distinguish the sine waves. We couldn't distinguish the sine waves because of how we were sampling. Well, we can't distinguish these because of how we are sampling with the blocks. So they're adding together. So the A effect is going to be contaminated by BC, just like the blue sine wave was contaminated by the red sine wave. But that's okay. We can filter or do things. Or maybe, why don't we just have some sense and pick our blocks a little differently, or choose our blocks such that if we're going to alias, let's alias things that we don't care about, and let's not alias things we care about. Oh, well, maybe we can do that. Yeah, that's a good thought. Let me try to do that. So I was postulating where we got to this bad spot was that we picked block 2. Okay, well, my first thought is, okay, I hate block 2. Let's pick block 1. All right? Let's see if that fixes it. Block 2 was a pain. So here's block 1. Here's those plus minus signs in block 1. So let's see what happens here. Well, let's look at A and BC again. They were problems before. Oh, well, they're just opposite signs. And B and AC, they were problems. Oh, they're just opposite signs, C and AB. So I really didn't do anything. You know, yeah, they're opposite, but okay, instead of adding effect, it's just going to subtract the same way. I still hit it in there. It's just, okay, it's like taking the red sine wave and multiplying by -1. It's still a bad thing. So I didn't help. My aliasing pairs weren't affected by my block choice. So how can we one of the questions is, we've got this plus and minus junk, drives us nuts, especially if we had 5 factors and, more levels. Is there a way mathematically with all this fun stuff we've learned, can we find these aliasing pairs without having to resort to pluses and minuses and looking at that stuff? And the answer is yeah. So what the book does, it shows you how to do it. And of course, it's going to go back to this mod operation that we did last week. So what they do, they say, look, set the identity equal to what you confounded when you created those blocks. So remember, we created block 1 and block 2 by confounding A, B, and C. So let's set I equal to ABC, which is a weird thing to do, but let's do it. And let's multiply by the A and the B and the C. And let's play, and let's do the mod 2 since we got 2 levels, and let's see what happens. So A times I equals A times A, B, and C equals A squared BC. Well, mod 2, remember the mod is the remainder. So if I mod each of these exponents with 2 mod 2, 2 goes into 2 once, there is no remainder. Big 0, so that says A to the 0. B to the first power, 1 divided by 2 is 0 with 1 remainder. 1 divided by 2 is 0 with 1 remainder. So if you mod this with 2, you only have BC left. Multiply by B, mod with 2, you still have a 1, that becomes a 0, that's a 1, you have AC. C times that, mod it with 2, that's still a 1, that's still a 1, that goes away and becomes a 0. So what you saw, look, remember, A and BC were aliased, B and AC, C and AB were aliased. Oh, okay, so we've got this weird mathematical technique to identify what's aliased based on the thought of we created this block structure by confounding that. Oh, okay, and even if we had chosen the negative of that, it works out the same. Yeah, so A and BC, B and AC, C and AB. So we've got a mathematical way to find these aliases. All right, so now let's see. So let's see if we can do something. All right, let's see. So based on 8.8, we had an example before. We had a two level experiment with 4 factors, A, B, C, and D. And we were making 2 blocks. So remember, we had our contrast that let us assign things to blocks was A, B, C, and D, because we were going to compound A, B, C, D. So 0 and 1 gave us our blocks. And let's see. Remember, if you recall, or I've got it in the Excel. Let's see. We had we had this data. So I'm going back. This is just the same example from last week. And we came up with A was marginally discernible, C was not, and our mean square error is kind of large, so we might want to do more data. So now let's see. And so I'm just reviewing that example. In fact, let's see. So what do I want to point do I want to make with it? Now let's bring it up here. We'll show you the point. So let's see. So again, this is problem 8.8. You saw this last week, how we picked things, what went into block 1 and block 2 by using that L, and if L was 0, it went into block 1. If it was 1, it went into block 2. And that let us come up with that setup where this was block, let's see, that was block 1, wasn't it? Okay, that's block 2. So I'm looking at block 2. See, A is in block 2, B is in block 2, C is in block 2. So I've got block 2. And this was my data. And let's see, we did an ANOVA on that. And we saw that A mattered and nothing else did. But A was close at 5%. And we worried that the error was kind of big, right, relative to some of the other errors, or over here either way, yeah, the mean square error is kind of big. So, maybe we needed more data to get a better handle on the error. So let's see. So let's look and see what was aliased. Let's see. So I've written it over here. And can we see that? So let's see. A, B, C, and D were aliased. C was aliased with ABD. B was aliased with that order, and A was aliased with that. So we've got a lot of our main effects getting aliased in this example that we picked last week. And how do I know that? Because I don't know that necessarily we're kind of just investigating right now what's alias. Let's see, how do we find that? Well, just like we said before, this block, to create these two blocks, we said we were confounding A, B, C, D. So let's do this goofy equation and multiply by A, B, C, D, some of these first order interactions too, and let's see what's aliased. So we multiply this times A, we'll have A squared, B, C, and D, and we mod it with 2, the A is going to go away. Okay, so A is confounded with B, C, D. I think you can get the pattern real quick. If I multiply by B in mod 2, B is going to go away. Yeah, B, A, B squared, C, D, yep, B went away. C is going to go away, D is going to go away. So each of the main effects are aliased with a second order interaction. Some, again, remember some weird second order interaction, B, C, D, I don't know what the heck that is. In fact, when we get to the Google little box, we'll talk about that. What does that mean? But, and then each of these first order interactions are aliased with another first order interaction. You can kind of see how that would work, right? AB times this is A squared, B squared with the CD left over, mod it with 2, the A and the B go away. Right? The pattern's real obvious real quick. Okay, so before, in chapter 8 we did this, we didn't know about aliasing. We didn't talk about it. So we just randomly out of the blue said, let's create 2 blocks by confounding A, B, C, D, and it doesn't matter, we're going to do them all anyway, so we don't worry about the aliasing. But now that we're only going to do 1 block, in other words, one set of samples, let's think, what have we done? Well, let's see. Our main effects are aliased with second order effects, and some of our first order are aliased with first order. Well, if we go back to this block assignment we had, we've got each of those second order effects that are aliases in this block. That's bad. We're polluting our A and B and C and D data with this, these higher order effects, just like we polluted our blue sine wave with the red sine wave. And you saw when we polluted it, and I did the FFT, I doubled the energy, even though I really only wanted the 4i, when I got 8i. Well, here, because I've confounded that I'm some of this stuff, D is polluted with ABC, C is polluted with ABD. This is not good. Because remember, we said if we pollute our errors and make our errors bigger than they should be, especially if we make this error bigger than it should be, we're not going to find what we were looking for, or we might find something that we were looking for and it was wrong. We've added we've added more variation to some factor that really wasn't due to the factor; it was due to ABC or something. And so this is not what we'd like to do. All right. So let's see. So what can we do? Are we stuck? What are we going to do? Well, let's see. We'll fix it. Let's fix it in this context, I guess. So we've got a half fraction. We're getting worse. We've got 5 factors, 2 levels. So now we've got A, B, C, D, and E. We're going to compound with the blocks. So let's see. Let's compound A, B, C, D, and E. Let's compound the highest order, and we've got a mod 2. So we're going to have 2 blocks. So in one block, if L is 1, 3, or 5, that'll create one block, and if L is 0, 2, or 4, that'll create the other block. So let's see. So I've created this, that's block 2. Oh my goodness. Okay, let me see. How do we get block 2? How do we get block 1? Let's see. Oh no, I guess I can't. I didn't show that with the Excel. Sorry about that. Okay, so let's see. Well, I can show you quickly. Like, remember this thing. If for the treatment that has just A high, A is 1, 0, 0, 0, 0. Mod that with 2, I get 1. So that falls in the block. Let's see. How would A, B, and C fall in the block? 1 plus 1 plus 1 would be 3. Mod that with 2, that would be 1. Oh, okay, that's block 1 also. So you can see each of these have fallen into this particular block we're looking at. Okay, so now let's see what each of, if these were the treatments we stuck in a block that was created by compounding A, B, C, D, and E, let's see what's aliased. So we didn't know, we didn't set it up, we just, we said compound ABCD with 2 blocks, let's see what's aliased. Well, just like before, remember you multiply each of the thing by the what you confounded, and then modded 2. So A times this is A squared BCDE. That leaves BCDE left over when you mod it with 2. B times that is A B squared CDE. Mod each of the exponents with 2, 1, 0, 1, 1, 1. Okay, you get the pattern again. C is eliminated, D is eliminated, E is eliminated. Oh, this is looking better, isn't it? So now I've confounded A with the really high order effect. It's going to have it's going to be a lot smaller here. I've confounded this first order with the second orders. I'm moving some of my confounding down to these little interaction terms that I care less about, and so that's better than confounding A with something like itself or something like that. So this is looking better. So our main effects now are aliased. I'm sorry, the compounded aliased with third order effects. First order with second order. This is a better structure than having first orders aliased with each other, having main effects aliased with each other, or having main effects aliased with the first order. So this is getting better. Now, how did I get better? Well, I randomly, I wasn't looking at the 4 factor anymore. I was looking at a 5 factor. I was just lucky in this case. I didn't do anything strategic. So one of the things they talk about is they rank these structures differently. And they give them what's called a design resolution, because you're able to look, how deep can you look? Can you look at main effects in first order before you start getting aliasing things, or can you look further down? So resolution 3 is, let's see, main effects are not aliased with other main effects, but main effects are aliased with first order, and first order with first order, like that first example we had. Resolution 4, main effects are not aliased with main or with first order, but first order or with first order. And then main effects 5, let's see, resolution 5, main effects are not aliased with main or with first order, and first order are not aliased with first order, like that one we just looked at. So you're getting better, you're getting more resolution. Let's see, so our example 8.2, that opening example, was a resolution 3. The one we did with the 4 factors was a resolution 4, and the one with 5 factors was a resolution 5. So it's better if you can do this. Now, we haven't done it. I mean, we just got lucky. Of course, maybe you'd say, well, add a factor. That allowed us to do that, but then expanded the number of experiments we had to do. So let's see.
Why does it start at 3? Resolution 3?
I don't know. That's an excellent question, because you'd think, there's some resolution 1s and 2s.
There's only been on this good.
Yeah, like, let's see, we could think that, I was going to see if they made a comment about that, because I thought that too, and I didn't follow it up. Let's see, I tell you what, let's think a second. Let's see, what could be worse?
Main effects, aliased with main effects.
I did, yeah, exactly. And let's see, main effects aliased with main, so that could be worse. And but I can't think of what 2 worses. I can think of 1 worse. I don't know. That's it. I'll follow that up. That's an interesting question. Why they chose those? Let's see. So let's see. So let's see. So let's investigate this one. This one where we had 5 factors or more, because that did seem to work out nicely with our aliasing structure at least. So let's look at one block of a 5-factor experiment that has 4 blocks, each of them having this many treatments. Right, because we get all the treatments, right? We're going to get all the treatments in 4 blocks, so 4 is 2 squared, so right. So if you have that many treatments in each of 4 blocks, you'll get 2F treatments. Yeah, so let's see. So example 9.3 is a quarter fraction, 1 block of a 2 to the 5th factorial experiment. And let's show that it's at least resolution 3, that main or aliased with first order and first order with first order. So let's see, we start with A, B, C, D, E, confounded effect in block 2. And let's consider choosing any other second order interaction to be confounded in block 3, like ABC. And then remember, block 4 is going to have an automatic confounding like we discussed with the planes. So we've confounded this to create block 2. We just chose that out of the sky to create block 3, and then block 4 will be automatically confounded. Yeah, so there it is. Remember how we did that? We found that the automatic thing was these two cross with each other. It was DE. So that's the automatically confounded factor in block 4. Okay, so now let's see. Let's set up our blocks. Let's see. Or no, let's analyze this. I forgot. I'm not going that deep. So, but remember, if we multiply D times DE and modded it with 2, you get E, or E times DE and modded 2, you get D. So this is bad. If we automatically confound this DE block in block 4, then D is aliased with E, and E with D. Yeah. So that's not a good setup. Well, okay, don't pick ABC, right? Let's pick ABD or ACE. Well, come on, think about it. If I did that, I picked ABC and D and E were confounded. Well, if I pick ABD, then C and E are going to be confounded. It's going to come out in the same math. I don't have to do it for you again. Or if I pick BCD, then A and E are going to be confounded by the same argument. So this is not something you want to do. Don't pick it this way. Okay, so let's see. What do they do? Let's see. So try it again. So let's choose to do two second orders to create our blocks 2 and 3. Instead of starting out with that ABCDE, let's start out with ADE in block 2 and BCD in block 3. Now let's cross them, mod 2. What's the automatically confounded thing? Let's see, A, B, C, D squared, E. Okay, so that's the automatically confounded thing for block 4. So we got that to create block 2, that to create block 3, this automatically created block 4. Let's look at the alias structure here. So let's see. In block 1, the block 2 alias, ADE, let's see. Multiply it by A, or BCD and ABCD. Yeah, so I'm doing them all, right. Oh, okay, I'm looking at them all. That's block 2, that's block 3, that's block 4. So multiply by A, and then mod 2 it, that's DE, and nothing was 2 there, so mod 2 didn't change anybody, A went away. Okay, let's see. Let's do it with B, let's multiply by B and mod 2 it, and C and D, let's see what's happening. So multiply by B, and mod 2 it, that didn't change, B squared, that was bad. C and mod 2 it, multiply by C, I get, A, C, D, E, mod 2, that didn't change. Multiply this by C, B, C squared, D, mod 2 it, that went away. You see what I'm getting at. So now let's see. You can kind of see what we're creating with this alias structure. Multiply by A, B, I'm just going down. I'm multiplying each of these identities for block 2, block 3, block 4 by each of the first main effects, each of the first order interactions. It makes a mess. But each time that I'm modding 2, each time I'm looking and seeing what's aliasing. So these are aliasing groups. So let's see. A was equal to either DE in the group 2, or block 2, ABCD in block 3, or BCE in block 4. Yeah, okay, so A looks like this. Yeah, B looked like that. Each of them got a first order, et cetera, et cetera. So the first group has 3, the second group has let's see, the second through 8 groups have 4 in it. Let's see, what am I saying? Yeah, see, this group has 3 things that are aliased together. This group has A, B, C, D, and all the way down to the first order. So there's 32 of these groups. So it's kind of a mess, but we can at least look and see what's aliased together. It's better. Let's see, we were trying to show that this is at least resolution 3, weren't we? Right, let's see. Yeah, so it was at least resolution 3. And it was, wasn't it? Because at worst, yeah, yeah.
Is it A the first order or just first
Yeah, so A is a main, and it's alias for the first order. So that was resolution 3. So at least it wasn't worse than that, But it was the other arrangement, wasn't it? this arrangement up here. And I guess that was a 4, this is a, yeah, oh no, that's right, yeah, so we got better that way, picking these 3 instead of randomly picking the A, B, C, D, E. You can see how this is getting hard though, because you can tell what I'm not giving you. I'm not giving you, how do you pick? You know, they're just picking these out of the sky. How do you choose to make, you know, I guess you play with it and see. It's not hard to do that math. You can play with it and see. Let's see. It's inquiry. Now we could also do this with the 3F experiments. You know, these have all been 2, low and high. Now if we had a 3, low, medium, and high, and then we're not doing a quarter fraction or a half fraction. You know, we're doing a third fraction because of the way the blocks have to be laid out with 3 levels. And so let's see. Here's that same example we had before from section 8.5, where we had 2 factors, 3 levels, and we had 3 different blocks. And on contrast, we were going to confound that. So L was X, the exponent here 2 times that, yeah, 1, 3. So when they're both low, I get a 0. When they're 1 and 1, I get a 3. Mod 3, I get L equals 0 again. So these are the treatment combinations that go in block 1. Those are 2, these are 3. Here, let's see. A is 2. X1 is 2, X2 is 0, so you have 2. Mod 3 would be 2 left over. That's how you get block 2. All right, so let's see. Let's examine this one. Alias structure here. So there was our I multiplied by A and mod. Let's see. And then they say in the book, mathematically, I want at least an exponent of 1 on here. So they square it, and then mod 3. So A is alias with AB. Square that. Let's see. A is mod 3. So A is alias with B. So this is a really bad. This is a really bad setup. If we were going to try to take, you know, before we use this, we used all 3 blocks last chapter. So what they're saying is, boy, if you try to do a 3F experiment here with 2 factors, and you set the blocks up like this, and you try to just pick 1 block, you did a disaster. You know, because you come down here and you look at your alias structure, and you've aliased a main effect with a main effect, and that's really terrible. So it's just not a realistic thing to do. Don't try to do a 3F experiment, a 3-2 experiment, and just pick 1 block. You know, you're just not going to be able to do that. You're going to have you know, more factors or more levels, or do something different. Don't try to make this arrangement, because you're just not going to be able to fix it. All right, so now let's see. So now let's do something realistic. See if we can make some sense out of it. Let's do 2 things. Let's look at example 9x, because it might, you know, at least you see if this stuff is real or not. So this is, so this goes back to that problem 8.8, where we had 4 factors. Blow it up just a little bit. We had 4 factors, 2 levels, low and high, and I've got 4 factors, A, B, C, and D. Okay, and so all this is the same thing you saw in problem 8, where I'm trying to assign each of the treatments, all the treatment combinations, to either block 1 or block 2, based on the idea that I'm confounding A, B, C, D. So remember, I have this contrast, A, B, C, D. So here everybody's low, L is 0, that goes to block 1. Here A is high, so 1 plus 0, 0, 0 is 1. I mod that with 2. I get a 1 left over, it goes to block 2, etc. So we've done this 3 times. This is the assignment of these treatments to blocks 1 or 2. We're making, and we've confounded one thing in the second block. All right, so now let's pick block 2, like we were doing in our discussion, the block that has A, B, C, let's see, A, B, C, and then D. Let's pick block 2. So there's block 2 only. Because for whatever reason, we've got long experiments, we can't do them all, we're only going to do this 1 block. And let's do an experiment. So my experiment is done. It's just, here's my data. Multiply by this factor, this factor, this factor, this factor, times whether A, B, or high or low. And I'm just letting each of the factors either be 1 or 2. That's all. The low is 1, 2 is high. But I'm magnifying them by this value. So for example, if I put a 20 in here, then a low A is going to be 20 and the high A is going to be 40. Put a 10 in here, low B is going to be 10 or high B is going to be 20. So what I'm saying is if I'm creating this data by just multiplying by this factor times either 1 or 2, or this factor times 1 or 2, that factor times 1 or 2, that factor times 1 or 2, and then this is my random noise I'm throwing on there to generate experimental noise data like I was measuring it goofed up. You can see that if with A being 20, it's obviously going to have a strong effect, right? It's most of the data. It's 20 times either 1 or 2. B's the next most, C's the next most, I'm sorry, D's the next most, then C, and then we're got quite a bit of error there. So this first experiment I did, I took that data. So looking at that data, looking at this equation is creating our data and these coefficients, we should expect that if we do an ANOVA, that we would think that A would matter, B would matter, maybe D, but you know, D is on the same order of magnitude as G as the error, and probably not D. So I took these coefficients, made me some fake data, just copied it in here. This little thing over here is my data maker. It just makes me fake data. Over here, did the ANOVA, and let's see what we got. Let's see. So, oh wow, you know, this stuff works. A matters, B matters, D, was close, wasn't it? It was on the same order of magnitude as the error, right? If we're talking about 5%. So, but you throw D out, but it was close, and C didn't matter. So you know, I wanted to do this example because, hey, look, this is a complete example of where we're at. We've got 4 factors, 2 levels. We're doing a screen. We've thrown out 1 block, and we've only got 1 block, so you know we were desperate. we're in bad, dire straits, but we were able to pick out the main effects. It worked. It actually worked. So in this case, our screening, our thought would be, well, you know, it looks to me like A matters for sure, B matters for sure, and look, A is stronger than B, wasn't it? Like we knew it was, and maybe D, and probably not C. So then, if we were going to repeat this experiment, I would sure think about doing a 2-factor experiment with A and B, and maybe I'd not do D, or maybe I'd do some further investigation to see if D mattered. I'd throw C out. C didn't matter. The heck with that. In my deeper experiments, when I'm going to go maybe not 2 levels, now I'm going to go 5 levels or something like that. Now let's play with it a little bit to make sure you're comfortable. So one of the things I did, we can play with it real time. Let's see. I made A little and C giant, and B I kept it the same. D I left it there, and then I lowered my noise. So let's see. That made this one over here. So let's see what happened. Yeah. Look, let's see. So in this case, A didn't matter, B mattered, and C mattered, and so did D. D looks better this time, even though I didn't change it. Well, why? Because it had less noise. Remember, we've always talked about it. If you've got less error, lower error, you know, you can dig out some of these other effects. Whereas in the first example, you know, the D got hidden in the error because it was almost the same order of magnitude. So we like this. We can go back and play. Let's see. Let's make some data. Let's make one. Let's put some more noise in there. Let's confuse D again. Let's put a little bit more noise in here. Make some more data. That's off the button. Then we can copy this. Let's Control C there. And let's see. Yeah, let me. Don't forget. Every time I forget to paste special, I must have not copied it. Try it again. See? There, I got it. Right now, let's see. Yay, paste values only. Yeah, so this time, see, we had more noise. What happened? B and C still matter, although C's, B's getting close to the limit. It's 5%, and that D mattered too still. Okay, so it's still in there. A got worse. Yeah, okay. Let's see. Let's play with it again. So let's make D stronger. I want D to stand out here. Let's see, 10. Well, no, I got rid of D. Oh, let's see what happens next. No, don't do that. Didn't like that, did it? Well, I didn't look that. Control copy. Here. Click paste special value. Now let's see. Did I make D stand out? Okay, yeah. I made D stand out. Looks like A and B and C now got less important. I make D big enough. Got enough air. Let's see if I reduce my air now. See what happens. I don't reduce it like that. Let's see. Enter. Now let's see how that works. Now you can see how this stuff. Now let's see. They all matter. B, C, and D matter in that case, yeah, because I reduced my error a whole lot. Even A kind of matters. You can even find A on that one. Very interesting. Yeah. Now it's an interesting thing to play with. All right, so now let's see. Let's do a realistic example. So now let's do this one so we'll understand, maybe get a feel for all of this. So let's see. So, and I'm going to use it. I'm going to use this same approach. So I'm going to use this problem 8A. I'm going to have 4 factors. I'm going to have 2 blocks, but I'm only going to pick one. So what is my experiment? What is my data? What is it? So the Google Little Box thing that we did at EPRI was that Google issued a challenge, and they wanted to get anybody in the world to develop a better inverter, because they see inverter technology as something that could have moved forward. At the time, it was 2.5 years ago, you know, a typical inverter was maybe 5 watts per inches cubed. I know that's mixed in SI and English units, but for some reason that's the way the inverter people do. So why would people care about inverters? Well, solar power, right? You got big inverter with your solar panels, or electric cars. You know, an inverter is going to take DC to AC. So you can see a solar panel. So Google was trying to encourage innovation in inverters, and why? Because they would also own or could share the intellectual property with the winners. And isn't it great to offer $1 million prize and get like 500 people around the United States to each spend, or around the world, if you will, to spend $1 million of research, and so then you can partner with them, right? So for $1 million, you got 5